You like that you're thinking of it in terms of exponential, so that's good. But if it wanted 8 to the 64th power, it would just write 8 to the 64th power, right?
Yeah.
We already have something that means that. But you're right, it is asking an exponential question. And the base of the logarithm is an 8. So the exponential base that we're thinking about should be an 8, like you said. But it's asking 8 to what power makes 64. So we can think of this as asking 8 to what power is making that 64. What exponent base 8 becomes 64? So what is it? 8 to what power makes 64?
2.
Yeah, 8 to the second power makes 64. Is that fair? So it is an exponential argument, but again, it's an inverse, so it's asking us the reverse. So as opposed to asking us what 8 to the 64th is, it's asking how do we get to 64 from an 8? Now, these other two are a little bit of trouble, actually, because 32 and 2, these aren't powers of 8. So 8 to what power is 32? We don't have a power of 8 that's 32. Or, 8 to what power is 2? I don't know, 8 to some weird power is 2. So those aren't being comparatively nice. So we look at, okay, are there ways that we can, say, manipulate these that might be more useful? Well, we have a list of properties. And those properties for logarithms are really based on what we know about exponents. For every exponential property we have, there's essentially a corresponding logarithmic property. So, for example, we do know that any base to the 0 power is equal to what?
1.
Is equal to 1. That exponential property yields a logarithmic property. It tells us that log base b of 1, no matter what that b is, b to what power makes a 1?
0.
0. So since we know b to the 0 is equal to 1, we know that log base b of 1 has to always equal 0. Remember from, it seems like a long time ago, from Thursday, that logarithms, I said, logarithms are our exponents. So this log base b of 1, it's asking for an exponent. What's the exponent in this argument? It's a 0. What is b to the first power? Oh, that's a weird question. But what's b to the first power?
B.
Yeah, b. Because again, our logarithms, well, again, this exponential property will yield a logarithmic property. It would be log base b of b, if we turn this into a logarithmic expression, equals 1. What power on b makes itself? Well, a 1 does. Fair? Once we get used to the idea that these logarithms are saying these exponential statements, that these go back and forth, I mean, these start to seem like kind of obvious statements, especially this one. These logarithmic statements are the same argument. We could have a little more fun with it. What if we asked, let's just go to straight to the logarithmic statements. What if we asked instead log base b of b to the n power? So if we looked at a specific example, if we had log base 3 of 3 to the 4th, that question asks 3 to what power is 3 to the 4th power? So what power would we have to put on a 3 to get 3 to the 4th?
4th power.
You'd have to put a 4 on it to get 3 to the 4th. It's a weird question, isn't it? And it should seem kind of like a weird question. It's like asking, I always like to ask, it's like asking, what is half of the double of 7? Well, half of the double of 7 is 7. But what is double the half of 7? It's still 7, right? The reason this is kind of weird is it has both the inverse and the straight function. It has both f and f inverse together. Well, what is log base 3 and exponent base 3 supposed to do to each other? They're inverses. They're supposed to undo each other. That's their job.
Can you explain why it's the 4, like the answer is 4?
Well, what is log base 2 of 8?
Hmm, 4? No. Yeah. I don't know.
2 to what power makes 8?
3.
2 to the 3rd power, right?
Yeah.
Okay. Well, when you did that, you kind of imagined that 8 as 2 to the 3rd, right?
Kind of.
And then you said, okay, 2 to what power made that 8? Well, what was the power on the 2 that made the 8?
3.
It was a
Okay.
3. Fair?
Mm-hmm.
And if we apply our definition says log base b of x, if that is equal to y, then b to the y is equal to x. This is our definition of what it means to be a logarithm. Fair? So if we say log base 2 of 2 to the 3rd equals what? Our definition says, we talked about that swinging over last week, says that 2 to the 3rd should be equal to 2 to the what? Well, what has to go in that box? If those are supposed to be equal. You turned your mic off, but I'm still going to make you talk.
3?
Yeah. 2 to the 3rd equals 2 to the what? Again, it sounds like a weird question. It sounds like a trap, doesn't it?
Yeah.
But again, if I ask you 2 times 7 divided by 2 is equal to what?
7.
Yeah, you might think that it sounds like a trick, but still 7, right? What is 5 plus 3 minus 3?
5.
5. What is 4 squared's square root?
4.
2. 4.
Now, you're right to pause on that one because we do have to be a little careful about plus or minuses with square roots, right? So, okay, what is log base 7 of 7 to the 3rd?
3.
Each one of those is a function and its inverse, right? So essentially, all of these ask the same question. what is f inverse of f of some value? And we know no matter what value we put in there, if f and f inverse are truly inverses of each other, their composition was always x, right? That's why this is actually referred to as the inverse property of logarithms, because it is just saying if we take an exponent base b and apply a logarithm base b, they will undo each other because that's their job. These two appear obvious. This one makes you think because you think it's a trap. And you want to do things like, well, if I square root the 4, I'll get a 2, but that 2 squared still turns into 4, right? So no matter what way you look at that, it still ends up being a 4. It takes longer to see this as, oh, that cancels out with that. Just like that cancels that cancels that cancels that. I don't like the word cancel there. It hurt every time I said it. I prefer undo because they're functions undoing each other. The only one that we should really say cancel with is this division. We could even take this one further and say, okay, what happens if we have b raised to the log base b of n? Or say 5 raised to the log base 5 of, well, I don't know, 25. What should that equal? Dun, dun, dun. What should that equal? Who's going to be brave? I know you guys are brave.
125.
It's going to equal, well, 125? 125 would be 5 to the third.
Oh. 3,125.
Ah, you're going nuts with it. Getting bigger.
25.
What should exponent base 5 and log base 5 do to each other? They should undo each other. And thus they should yield that 25. But even if we wanted to walk through it, if we isolated log base 5 of 25, again, that asks 5 to what power is 25? 5 to what power makes 25, Justin? What power on a 5 makes 25?
2.
2. Then what's 5 squared? Well, I'm almost asking the reverse of the question I just asked you, right? And again, that's the point here. The logarithm is turning it into the exponent. Well, now that it's an exponent, 5 to that exponent gives us back our 25. If I asked you what 13.7 divided by 2 times 2 is, what is 13.7 divided by 2 times 2?
13.7.
Aaron, when you found that 13.7, did you divide the first 13.7 by 2?
No.
And get what, 6.85? No, you didn't. You went, hey, division by 2 and multiplication times 2 are inverses. They undo each other. So I'm just going to be left with the 13.7. Now, visually, you're really super used to that. You hardly even think about it. Are you visually used to seeing, I don't know, 2 to the log base 2 of 8.3? No. But exponent base 2 and logarithm base 2 are inverses of each other. So what are they going to do?
Undo each other and leave 8.3.
They're going to undo each other and leave the 8.3. Exactly. If we have 5 to the log base 5 of 173.8, what's it going to yield?
$173.8.
173.8. We could have a little more fun. How about the natural log of e to the 0.74?
0.74.
Yeah, natural log is log base e. So just like all the others, log base e and exponent base e undo each other, yielding 7.4. Now, a very reasonable thing to be thinking here is like, well, is how often is somebody going to ask us that? How often is somebody going to give us that kind of same base, same base of the exponent, same base of the log, problem? How practical is that? And to answer that, I'm going to, of course, ask you guys a question. I'm always ending up asking you guys a question. How often do you end up taking the half of the double of something? I want you to think about that for a second. What's that, Justin?
I was going to say never really.
Okay. I like that you answered that, even that you know it's a trap, right? Solve 3x plus 4 equals 8. What do you do to solve that?
Add 4 and divide by 3.
Well, you subtract 4 and divide by 3. You're right.
Yeah.
So what do? You find 4 less than 4 more than 3x. Right? Then what do? Then you ask, what is 1/3 of the triple of x? Right? So how often do you find the half of the double of something?
It's all the time.
All the time. So when are we going to use this fact? Well, if we're trying to solve something that says e to the 0.3x equals 7, I'm going to go, what am I going to do to solve that? Well, we're going to ask the natural log of e to what power is the natural log of 7, so those will undo each other. It won't happen naturally. We will do it on purpose, just like we invoke the inverse operation of everything else, so we can solve. Does that make sense? It just takes a while to see it. Now, notice I didn't write the exponential version of those. And I'll show you why. The exponential version of these is that b to the n is equal to b to the n. That's the exponential version. But the point of all this was kind of to talk about those first three, because they're the ones that give us the weird properties that we want to use on this problem. So how comfortable are you with the idea that this x to the third times x squared is equal to x to the fifth? Have you been doing that for a long time? Really happy with it? You guys know these questions are traps. I like that. Yeah, I can see you guys go, oh, what's he gonna do? But x to the third times x squared is x to the fifth. How do we get that? What do you do with the 3 and the 2? I'll answer that. You added them together, right? So what happens to exponents? What happens to our exponents when we multiply things? Well, we add the exponents, right? Okay, so what happens to exponents? Logarithms ask about exponents. That's their job. The logarithm is the exponent. The logarithm is the exponent. The logarithm is the exponent. What happens to exponents when we multiply two things together? Well, what do? You took the exponent of the first one and added it to the exponent of the second one. Is that fair? These two properties are the same property. One is expressed as an exponent. The other is expressed as a logarithm. But they say the same thing. What do we do with the exponents when we multiply? Oh, you added them. 3 plus 2. What do we do with exponents when we multiply? Oh, we add them. We could also go the other way. What if we have two exponents added? Well, that came from a multiplication. So if we wanted to handle this problem a different way, if we had log base 8 of 64 plus log base 8 of 32, we could turn that into log base 8 of 64 times 32 if we wanted to. I'm not saying we do want to. Don't get me wrong. I'm saying we could. Fair? Let's look at a smaller example. If we took, I always love that log base 2 of 8. If we took log base 2 of 8 and added that to, let's say, log base 2 of, let's just go with 4. What is log base 2 of 8? I know, I ask you guys that a lot. It's still 3, right? Log base 2 of 4, well, 2 to what power is 4? 2 to the second power is 4. So this would equal 5. But what if we use this property and said, okay, the log base 2 of 8 times 4. What's 8 times 4? 8 times 4 is 32. Well, what do we know about 32? We might know that 32 is 2 to the 5th power, because it is. Well, log base 2 of 2 to the 5th is, oops, yeah, that's horrible, is 5. Same 5. Fair? Now, how could we have gotten that 2 to the 5th if we didn't know? Well, that 8 is 2 to the 3rd times 2 squared. What's 2 to the 3rd times 2 squared? It's 2 to the 5th. Well, how do we get that 2 to the 5th from this property? Well, how do we get that 5? It's the same 3 and 2. It's just, are you dealing with the 3 and 2 in the logarithmic argument, or are you dealing with 3 and 2 in the exponential argument? It's the same argument, just a different side of the coin. I don't have Andrew here to ask, why is that helpful? Well, let's say, for sake of argument, you have, I don't know, log base. Well, let's actually look at that 8. Let's go back up here. Let's say we have log base 8 of this 32. And I want to change this to an addition for this example. And I'll get rid of the 5. So log base 8 of 2. Well, log base 8 of 32 is some weird number, somewhere between 1 and 2. What power of 8 makes 32? Well, 8 to the first power is 8. 8 squared is 64. So it's somewhere in between there. Log base 2 of 8. What power do you have to raise 8 to make 2? Well, technically you can raise it to the 1/3, I suppose, because the cube root of 8 is 2. But I don't want to put a 1/3 in there, and neither would Andrew. But this property says that we can turn that into log base 8 of 32 times 2. This property up here. The log of a product is equal to the sum of the logarithms. So the sum of the logarithms is equal to the log of the product. So that's the log of, well, 32 times 2 is 64. What's log base 8 of 64? 2. Made this problem that we couldn't really approach into a problem we could. Fair so far? Crystal, how you feeling about that? You got that look in your eye. Justin, how about you? So fairly quickly, we can actually do these others. What did you do when you divided? Well, you subtracted the exponents. So we get a division property. What happens to the exponents when we divide? Again, that's a translation of what that says. Log base b is what's going on with the exponents when we divide. Well, you take the exponent of the top one and you subtract the exponent of the bottom one. So we could use that here if this darn 5 wasn't in the way. So we'd have to figure out what to do with that 5 first. But we'll get to that in a second. And again, this property, these are just the same argument, logarithmic argument, exponential argument. I want to do this one first, and then we'll do that whole problem. What happens when we have a power raised to a power? Well, you took those two powers, instead of adding them, you multiplied them, right? You didn't get a negative. You multiplied them. So, again, what happens to the exponents when you have something raised to a power? Well, you take one of the exponents, the exponent on your thing, and you multiply it by the other exponent. Again, that's that exponential property in its logarithmic form. So as I said, this 5 is kind of in the way, right? What could we do with that 5? Well, if we wanted to, we could put that 5 up there and say this is log base 8 of 2 to the 5th. If we wanted to. That seem reasonable?
I'm not sure if I understand why you can do that.
It's weird, isn't it? I could, we could go through a proof. X squared to the 3rd equals, well, I don't want to say X squared to the 3rd. X, Richard's not working. And say that, no, it's not working that way. Say if we had, X to the A to the N, and we wanted to, show that that's equal to, I had to show what it's equal to. We know that's X to the AN, right? We know that's true, right? Well, I'm going to do a little bit of notation change here. Let U equal X to the A. So I can write this as U to the N equals X to the AN. And is that what I wanted? That's not what I wanted. Yeah. I don't think the formal proof is going to help anyway. Let's do it a different way. Let's say we have log, let's go with base 2 because base 2 is nice. Say we have log base 2 of 8 squared. Now we know that 8 is equal to 2 to the 3rd, right? Right? So that's 2 to the 3rd squared. Log base 2 of 2 to the 3rd squared. Well, what is 2 to the 3rd squared? What are you doing with those exponents? Well, you're going to multiply them, right? 2 to the 6th. What is log base 2 of 2 to the 6th? Again, log base 2 and exponent base 2 cancel. It's going to yield the 6. Again, watch the 2 and the 3. We multiplied them, right? But we've got this nice property. Let's say we use that property. Going to take that 2, bring it down in front instead. So 2 times that log base 2 of 8. Well, what's log base 2 of 8? Well, it's 3. It's that same 3. What's 2 times 3? It's the same 6. So again, are we multiplying the exponents while they're still exponents? Or am I multiplying this exponent of 2 by the exponent I'll get when I do that? It's the same 2 and the same 3. Justin, is that better?
Yeah.
And the unsure, yeah, I totally buy. It's a big manipulation. That exponent comes down as a multiple. And you can kind of look at this argument here with the 2s and the 3s and go, okay, that seems true, but it's a surprisingly massive property to be able to turn this exponent into, oh, now we're just multiplying by it. So some of the skepticism there is good. But again, in this exponential argument, what happened? Well, the powers turned into multiplying, right? So what's happening over here? The power is turning into a multiple. It's just doing it in the weird log language. Can we do cool things with this? Oh, absolutely. If I ask you what log base 2 of the square root of 8 is, That square root has to make you go, ugh, right? Well, that's log base 2 of 8 to the 1/2. Well, crud, what can we do with this 1/2? Ding, ding. So 1/2 times log base 2 of 8? Absolutely. What's log base 2 of 8? 3. We just turned something as nasty as a square root into multiplying by 1/2? You better believe we did. By the way, could we also have taken log base 2 of 8 to the 1/2 and said that that's log base 2 of of 8 to the 3rd to the 1/2, which is the log base 2 of 8 to the 3/2. Oops, sorry, log base 2, 2, 2. And then said, oh, that's 3/2, and gotten the same 3/2 because we multiplied the same 3 by 1/2? Absolutely. It probably, tell me if I'm wrong, seems more reasonable here, multiplying those together, and seemed almost crazy to be able to do this. Is that right? Aaron's like, no, they both make sense, right? Or neither of them make sense.
No, I like the other way. It just feels simpler and cleaner.
Oh, once you're comfortable, this is so much better. But at first, this is usually more comfortable because you're used to seeing this. Your eyes go, I've seen that before, that's cool. This just looks like, am I allowed to do that? But Aaron, you're absolutely right. Once we get comfortable, it's like fractions. Once we get comfortable with that, oh, it's a much cleaner, much nicer, much simpler way to handle things. And this is why we like and have logarithms, is because they give us so much power to manipulate things in ways that other stuff doesn't. The disadvantage is it looks really weird to do until you get enough practice doing it that it eventually seems natural. Justin, is that fair? It'll take some time. So I want to tell you what, before we guys, this is a day on a big problem, but that's okay. We got to talk about all kinds of cool stuff. But when I look at this problem, 64, 32, and 2, those are all powers of 2. This is log base 8. 8's a power of 2 as well, of 2 to the 6th plus the log base 8 of 2 to the 5th minus 5 times log base 8 of 2. Is that a fair argument? Now, whether that's useful or not, it's true. What can you tell me about those two expressions?
They undo each other.
Yeah, they're the same. Whether you want to pull that 5 down or pull this 5 up, these two subtract away. And we're just left with this first statement. Well, heck, we already decided what that first statement equaled, right? But we can certainly express it as 8 squared if we want to. And say, hey, that's a 2. Or we could bring that 6 down and say 6 log base 8 of 2 And what's log base 8 of 2? Well, it's the cube root of 8 makes 2, so it's a 1/3. 6 times 1/3 is 2. I wouldn't make that argument if I were you, but it certainly works.
I think I'm starting to get.
And it's just the ability to kind of throw these things around. Well, what if you didn't see that those subtracted and you did these two first? Well, as I said, that's log base 8 of 64, which is 8 squared, which is nice, times 32. Well, 32 is 8 times 4, right? Pull out that other 8. 5 times log base 8 of 2. Okay, so this is log base 8 of 8 to the 3rd times 4. That's handy. Minus 5 times log base 8 of 2. I'm just looking at different ways to do this. Well, this 8, those 8s are nice. Let's separate that off. Log base 8 of 8 to the 3rd, plus log base 8 of 4, minus 5 times log base 8 of 2. Log base 8 of 8 to the 3rd is 3. Plus, well, this is still kind of irritating over here just because of that 2. But let's put that 5 up there. Why not? We're certainly allowed to. So log base 8 of 4 minus log base 8 of 2 to the 5th, which is 32. Okay, so that's 3 plus log base 8 of, well, we could certainly divide those if we wanted to. 4 divided by 32. I'm starting to enjoy this less, but oh, don't the 4 and the 32 divide? That's nice. So that's 3 plus log base 8 of 1/8. What power do you have to raise 8 to get 1/8? 8 to what power is 1/8?
-1.
-1. 3 plus -1. The same 2. Again, I wouldn't recommend that path. It's longer and more irritating. But does it work? Absolutely. Now, before I let you go, I want to tell you what I think, personally. I might be biased. What I think is the funnest part of this. Going through all this down here, I did it fast. I did it kind of fast on purpose, just because we have to go mostly. But you probably got a little bit of a headache during that, right? Technically speaking, there is absolutely nothing I know about that you don't right now. There's not some secret to that I'm holding back from you just so I can, I don't know, be taller. What's the difference between being able to throw them around that way and looking at them like it's just a jumbled mess? What makes the difference?
One's quite a bit easier.
Well, what makes the difference in having it be a mess and having it be something you're throwing around and playing with like building blocks?
Knowing the rules of how it works.
You know the rules. They're right up there in the corner. Crystal, what were you going to say?
Just being comfortable and confident with them.
Well, how do you get to that point?
Practice.
Practice. How did you get good at throwing your fractions around relatively well? With practice. Why is it that if somebody writes 3x minus 5 equals 18, you start subtract or adding that 5 and dividing that 3 off without even thinking about it. Because practice, because you've seen it before and gotten good repetition with it, right? How do we get used to looking at log base 5 of 8x equals 3 and going, oh, that's 8x equals 5 to the third. So 8 to the x equals 125. Oh, so I can take the log base 8 of both of those and say that's x equals the log base 8 of 25. How do we get there? By seeing it over and over again. Even better, going, I want to get this x out of there. We'll talk about this tomorrow. So I'm going to use a natural log because I like natural logs. But that allows that x to drop down in front because I have a logarithm there. And then we can divide those off because they're just numbers. Takes practice. One of the things I don't like about this section in the homework is there's not enough of this little throwing things around practice. Go in, do some of those little manipulation problems repeatedly. Have it give you extra ones until they're just thrown around like they're your toys, because they're your toys. Fair? All right. Go do that. Was this helpful today? Going through these properties this way? We kind of went backwards through them, but that's okay.
Yeah, I found it helpful.
Okay. Bring good questions tomorrow. And have a wonderful day.
Hey, before you go, can I ask you a question?
Of course.
I don't know. I use a late pass on the 5.3 and the 5.4 homework. But I didn't realize that it expired yesterday. Is there any way that you can open those up for me so I can finish them?
I gave you a bunch of late passes back.
I noticed that, but I let them go gray, so it won't let me use them on there.
Right. So yeah, I can absolutely do that. Let's see. All I have to do is remember how. Which one?
Oh, it was 5.3 and then 5.4. I was almost done with 5.3 and then 5.4 I was about to start, and I'm gonna do most of what I'm like back on today.
Okay. Let me check, make sure that worked. Okay, that should have worked. If not, let me know.
Okay, sounds good.
Can you, while I've got you here, I want you to check.
Yeah, that I might as well. Yeah, that worked.
Okay, perfect.
Okay, and then one more question. If I totally flaked on my hand in homework for the past 2 weeks. If I send it into you, like today or tomorrow, can I get some credit on it?
Yeah, wouldn't hurt.
Okay. All right, I will do that. Yeah, I'll see you tomorrow.
Okay.
Thank you so much.
Mm-hmm.